in the webinar series on the SAR data processing conducted by Indian Institute of Remote Sensing, ISRO, and CEO's working group on capacity building and data democracy. So in this webinar series, the major topics are the SAR remote sensing concept, which will be delivered today, in which it includes the SAR geometry, imaging modes, SAR resolution, geometric distortions, layover, shadow, foreshortening, and SAR image properties and interpretation. On 13 May, the topic will be SAR data processing 1, in which we include the SAR data processing concept, pulse compression technique, synthetic aperture concept, range cell migration, and range Doppler algorithm. So basically in the SAR data processing 1, we will mainly focusing on SAR focusing algorithm, means how to convert the raw data of the SAR to the process data of SAR. In the 21st May, the webinar will be on the SAR data processing 2, which includes mostly the geometrical and radiometrical techniques of the SAR data, which includes the geolocation, geocoding, orthorectification, and the stacker filters. And the last lecture will be on the SAR interferometry, which will be delivered on 28th May. It will include the interprogram generation, baseline concept, across track and along track interferometry configuration. So in this webinar series, we will basically touch upon mainly the basics, then the SAR data processing, and the application part of the SAR interferometry. So in today's webinar, we will discuss the SAR remote sensing concept. Now, what are the principles of the remote sensing? So basically, the remote sensing is divided into optical infrared remote sensing, thermal infrared remote sensing, and microwave remote sensing. So in our satellites, what we will do in the optical infrared remote sensing, mainly we collect the reflected sunlight in the optical range of 0.4 to 0.7 micrometer and near infrared. Okay, and in the thermal infrared remote sensing, mainly the emitted radiations we will observe through the thermal sensor. So mainly the remote sensing will be done in the thermal region. Now in the microwave remote sensing, basically the backscattered radiations in the microwave regions are sensed by the sensor. Optical wavelength uses lens and mirrors for focusing, but in the microwave region, we uses the antenna for focusing. So if this is our electromagnetic spectrum, so this is called the optical wavelengths up to from the visible, near infrared, short infrared, and thermal infrared. This is the optical wavelengths. And this microwave region are non-optical wavelengths. Why optical wavelengths and non-optical wavelengths? Because in optical wavelengths, we will use lenses and mirrors for focusing any image. But in microwave region, we consider the radar to focus the image. Okay, so this is the basically in all satellites, these three types of remote sensing we will do. So in microwave region, there are different band designations, which includes the Ka band, K band, Ku band, X band, C band, S band, L band, and P band, and different wavelengths. So now what is microwave remote sensing? So basically the microwave remote sensing have active remote sensing also and passive remote sensing also. So active remote sensing will be done through the active sensors. So what are the active sensors? It is the synthetic aperture radar, which is called SAR. So it is the imaging technique. So in the remote sensing, we can do either imaging or non-imaging. Okay, so imaging data is of two-dimension data, but non-imaging data is the profile data, single one-dimension data. So our active sensors which uses microwave vision are synthetic aperture radar, spectrometer, and altimeter. Synthetic aperture radar is used for imaging. Spectrometer is used for non-imaging. It is used for backscatter information for the ocean surface and for studying the wind speed and direction near the ocean surface. Altimetry is also a non-imaging technique which measures the surface topography. And in the passive sensor also uses the microwave region. So what are the passive sensors? Passive sensor in the microwave region is the radiometer. So it senses the microwave emissions from the Earth surface. So these are the two sensors. Active sensors are those sensors which uses their own energy to illuminate any surface. So active sensors are like radar. Means if we simply use the radar, then it is an active sensor. But if we use for imaging, then we use the synthetic aperture concept for imaging. That is called the SAR. What are the passive sensors? Passive sensors use the sun energy for illumination of any surface. Okay, so radiometer is a passive sensor and used in the microwave remote sensing for doing the passive imaging. Now, what is SAR remote sensing? SAR is the imaging radar. It is an all-weather observation system. It is an active system sensitive to dielectric properties of the medium. Means dielectric property means water content and humidity. If it is in the any natural object like soil, if it is in the soil, then it will detect the soil moisture from the soil, and it is sensitive to the surface roughness, and SAR response increases when the moisture or surface roughness increases. If in the soil the moisture and roughness will be higher, then we have the higher response in the SAR image. Means in the SAR image that object will appear as a bright object. It has the penetration capability. It is sensitive to topography. Means it is very much sensitive to the terrain topography. Means it is for the mountainous region. If there any slope is there, then it is very much sensitive. And it has the colorimetry capabilities also. It is sensitive to metallic and artificial objects due to its because it is sensitive to dielectric properties of the medium. It is sensitive to the geometrical structure of the object. Okay, and what are the limitations? Limitations are the complex interaction. So because it involves very much physical formula, very much physics behind every process. So understanding of various scattering mechanism needed. So understanding of the SAR image is very much difficult. So we have to have little bit knowledge of the physics behind it. Means what is how the electromagnetic radiations are interacting with the particular object. So accordingly, we have to infer and interpret the SAR data. It has the speckle effects. Since SAR is a coherent device, so there will be the interference within the SAR system. So it will generate a noise which is called the speckle. So this speckle noise will have the difficulty in the visual interpretation. So this is the very much limitation in the SAR because it has the speckle noise. So we have to do some post processing according to our needs as per user requirement. They will apply the speckle filters and clear the noise. And it has very much topographic effects also. Means due to the mountain and terrain, it has very much geometrical distortions. So we have to correct that geometric distortions. Now, what is the potential of SAR? With respect to the optical imagery, means like satellite like Cartosat 1, Econos, LIS 3, LIS 4, these all are the optical satellites. So because that optical images are passive sensors, so they will use sunlight as the source of the illumination. So they can operate only in the day. But SAR is an active instrument, so it does not require the sunlight as a source of energy because it transmits its own energy to illuminate any surface. So it has day-night imaging capacity, and it is insensitive to cloud cover. So it can penetrate through the cloud. So any in the monsoon seasons, the optical satellite cannot image the Earth's surface, but our SAR sensors can image the Earth's surface. So during the flood time, and mostly the atmosphere and is covered with the clouds. So that time we cannot use the optical satellite. That time we will use the SAR satellite and for the flood mapping. And so the day-night imaging is twice we are getting the data, and because it is insensitive to cloud cover, so it has the 5 times capability of the imaging. So total it is 10 times more images are available. So it is a multi-incidence, means for multiple incidents we can have the we can have the SAR sensors, means we can have the different look angles and different SAR images. And we have the multi-resolution, means optical satellite resolution is single, but in our SAR we can have different resolution in a single SAR sensors, means different imaging modes can provide different SAR resolutions. Now, what is RAR and what is SAR? RAR is a simple radar which is called a real aperture radar. So it uses the microwave region and energy emitted across track in the range direction, and return time measure the slant range and amount of energy, means scattering. So a simple radar, what it will do, it will emit the electromagnetic radiations, and that electromagnetic radiations are received by the radar with some time delay. From the time delay we can calculate the range. So simple radar measures only range, so it cannot produce the two-dimension high resolution images. So synthetic aperture radar uses the concept of the synthetic aperture. So it will use the microwave region and produce the high resolution in both range and azimuth. So higher resolution in the azimuth direction is done by the extended antenna simulated by the forward motion of the platform. So this SAR platform will move in this direction. So during the motion of the sensor, it will generate or it will simulate a large antenna to have a better azimuth resolution. So this is called the synthetic aperture. Due to the motion of the sensor, it will simulate a large antenna, and that large antenna will have the high azimuth resolution. So we have the high resolution images both in the range and in the azimuth direction. Okay, so that is the main difference between the real aperture radar and synthetic aperture radar. Real aperture radar does not use the concept of the synthetic aperture, means motion of the sensor, but synthetic aperture radar is a simple radar, but it uses the concept of the motion of the SAR to image and to generate a high resolution image in range and azimuth direction. Now, what are the SAR transmission features? So first is the frequency, means at which frequency we are illuminating the surface. Means if we are emitting if a SAR is emitting a electromagnetic radiation, so at which frequency it is emitting. And what is the propagation direction, means in which direction it is propagating, means look angle. And at which power it is illuminating, means it will impact on the image quality. If the power requirement are high, then we have the different image quality. And fourth is the polarization, means SAR has the capability to have the means to have the electric field vector in particular direction. So this is the electric field vector if it is perpendicular to the, if it is in the horizontal direction with respect to the propagation of the wave, then it is called the horizontal polarization. When it is perpendicular to the motion of the wave, it is called the vertical polarization. So SAR has basically four type of transmission features, means what is the frequency it is using, what is the propagation direction, means what is the look angle, how much power it is transmitting, and what is the polarization. So these four are the key parameters which we should keep in mind in the SAR transmission. So what is the synthetic aperture radar or SAR? So how it functions? It transmitted from the antenna, means electromagnetic radiation will be transmitted from the antenna. So these are called the pulses. So it will emit the electromagnetic radiation. So these electromagnetic radiations travel through the space and it interacts with the earth surface. Means if there is a tree, it will interact with this trees. Then these electromagnetic radiations are backscattered towards the sensor. So some of the energy is backscattered towards the sensor, and some of the energy will reflected away from the sensor. Okay, so this backscattered energy, if it is collected by the sensor, then we can get a signal. Otherwise, we cannot get a signal. Okay, which is reflected over. The signal which are not captured by the SAR, it's called the specular reflection, because all the electromagnetic radiations are reflected away from the sensor. That are called the specular reflection. So it will capture the backscattered radiations. And the backscattered energy is received by the SAR and it amplified as a voltage and recorded as a digital number. So this energy, backscattered energy, is captured by the SAR receiver. So and these energy is amplified as a voltage, and this voltage is converted to the digital number using the analog to digital converter. So the SAR image, what we get, this is the raw data what we are getting in the ground. Means it SAR transmit the electromagnetic radiations and backscatter energy is collected, and that energy is recorded, and it will again transmitted to the ground stations, and the ground station receive this raw data. Now this raw data, you can see no information in this one. So we are using the SAR data processing techniques, which are the signal processing technique, to focus the data. So after using the SAR data processing concepts, we can focus this data from this to this level. Okay, so this is the raw SAR data, and this is the focused SAR data. So in the next webinar series, we will discuss about the SAR data processing concepts. Okay, in this webinar, we will see only the basic concepts of the SAR. So SAR is it is a side-looking radar system which makes a high-resolution images of the Earth's surface. Okay, and the continuous strips of the ground surface are illuminated to one side of the flight direction. So if this is the SAR, and it can it have a motion in this direction, so it illuminates the Earth surface like a torch beam, as we use in our home torch. Then like same concept, it will illuminate, and this is called the SAR beam or footprint on the ground. So this is called since this is an active sensor, then it will illuminate the Earth surface with the SAR beam or radar beam with some angle. So this angle is called the theta angle. This is called the height, and this range slanting line is called the slant range. So this is the velocity, this is a look angle, this is the height of the sensor, and this is called the footprint. Then the signal is recorded, and digital signal processing technique in the ground are used to focus the image and obtain a high resolution image. So how the SAR image formed means with the motion of the SAR, continuous strips of the ground surface are illuminated to one side of the flight direction. So it illuminates the ground, and this data is transmitted back to the ground. So this signal is recorded and it is passes to the ground stations. So this is the data what we will get in the ground station. So this is called the range direction. This is called the azimuth direction. This is the flight direction. So this is range. This is azimuth. And how the data is acquiring this, like first pulse it will receive, second pulse. Pulse means electromagnetic radiation energy. So we can have, because it is in the digital number. So this is first pulse, second pulse, third pulse, fourth pulse, like that. We can get this data. These SAR raw data we will get on the ground. So this SAR raw data is basically a complex data. Okay. So in the SAR data processing, we will use the complex data for processing. Okay. So the across track direction distance is called the range, and the along track direction is called the azimuth. So what is the principle of the synthetic aperture radar? So it absorbs the strength and the time delay. So in two basic things it will record. One is the backscatter energy, means the energy what is backscattered towards the sensor. It will record that energy plus the time delay. How much time is delay between the transmission and receiver? Means it transmit the electromagnetic radiation, then the radiations interacts with the earth surface, then how much time it will take from here to there, means from the receiver to transmission. Okay, so that time is recorded, and with the help of that time we will calculate the range. So time delay is equals to 2r by c. Okay, so we will use the simple formula, time is equals to distance upon speed, and we know that electromagnetic radiations are traveled in the speed of light. So time is equals to distance upon speed. Then we calculate the range as Ct by 2. Okay, so because 2r is due to, because it is traveling twice this distance. So this distance is 2 of r, and c is the speed of light, and time is time taken. So putting in this formula, we are getting the range as Ct by 2. Okay, so this is the range which we calculate for the SAR sensor. So the SAR has basic two information. One is the backscatter energy, which we will get in the form of image. In the image, we will get some energy, which is called the backscatter energy. Apart from the backscatter energy, we get the many more parameters in the meta file, in which the range is very much crucial parameter, because it will directly calculate the distance from the SAR to the target. Okay, so this range and the backscatter energy is calculated by the SAR. So normally the optical sensors has a single resolution, but the SAR has the two resolution, means in the range direction and in the azimuth direction. So the resolution in the range direction is called the range resolution, and the range resolution mainly depends on the pulse bandwidth, means at which bandwidth which we are transmitting the electromagnetic radiation. So initially I have told you about the frequency, at which frequency we are transmitting, frequency and bandwidth, at which bandwidth we are transmitting the SAR signal. So from the formula of delta R from the previous slide, C tau by 2, and this is time is inversely proportional to the bandwidth. Okay, so we can substitute tau as 1 by b, then our range resolution will become C by 2b, means it is inversely proportional to the bandwidth. Okay, so bandwidth is higher, then this rho r will be smaller, means this value is smaller, means we are getting a better range resolution. So if the bandwidth is 250 megahertz, then what we are getting the range resolution as 0.6 meter. So if we have this bandwidth 75, 150 and 750, then the resolution what we are getting corresponding to this bandwidth is 2 meter, 1 meter and 0.2 meter. So this is the range resolution, which directly depends on the what electromagnetic radiations which we are illuminating at which bandwidth. Okay, and second is the azimuth resolution. So this azimuth resolution is obtained by the synthetic array approach. Means SAR uses the synthetic array approach, which I have told, like with the motion of the SAR sensor, a long antenna is simulated, and this large antenna will improve the azimuth resolution. For a strip mode SAR, the azimuth resolution is given by L by 2. L is the antenna length, and it is the half of the antenna length. So if the length of the SAR antenna is 12 meter, then we can get the azimuth resolution up to 6 meter. Okay. So these are two concepts of the range resolution and azimuth resolution. These concepts we again read in detail in our upcoming webinar series. Okay. So what are the imaging modes in SAR? So first is the strip mode SAR. So what is the strip mode SAR? It is the continuous image is formed with the motion of the SAR. So it is a means if this is the SAR sensor, then in the azimuth direction it is the synchronous imaging. Means as the SAR is moving, then it will illuminate the surface corresponding to the for motion of the SAR. Okay. So no steering in azimuth direction during imaging. Means it will have no steer. Means it will look as it is. It is parallel to the motion of the SAR. Okay, so this illumination is always towards the Earth surface. So no steering is there in the strip mode SAR. It is a synchronous imaging, and it forms the long imaging strips. So if we want a long imaging strip, then we use the strip mode SAR. So what are the limitations? It has the azimuth resolution of L by 2. So in the previous slide, I have told you about the azimuth resolution is L by 2. So that is the maximum resolution for the strip mode case. If we want the better resolution, then we have to change our imaging capability. Okay. And the second limitation is the swath is limited. Means this swath is very much limited in the strip mode SAR. Okay. So first is it has the azimuth resolution limited, which is the L by 2. Means if the SAR antenna is of 12 meter, then maximum it can have only 6 meter resolution. But if we want the high resolution SAR images, what we will use the spotlight mode. In the spotlight mode, the sensor steers its antenna through the squint angle to continuously illuminate the scene being imaged. So actually, this synthetic aperture, if longer will be the synthetic aperture, the better higher azimuth resolution we will get. So if we increase the synthetic aperture or simulated aperture, then we will get a higher resolution. So what is the technique to use the higher synthetic aperture? If we can look this surface for a longer duration of time. So if we steer our antenna and rather to look at every scene, we will concentrate on a particular ROI and we steer our antenna to a particular scene. So we can see for that particular scene, the synthetic aperture time will increase. So because the SAR is seeing this to this portion for a longer duration of time, so we can get the higher azimuth resolution depending on the time. So longer it will see the image with the steering capability, then higher resolution we will get. So L by 2 we can get a better resolution, better than L by 2. Okay, in the strip mode case we can get the 6 meter, but if we can have the spotlight mode, then we can get up to the 1 meter resolution or better than that also. And what are the limitations? Limitations are it has the limited strip length in the azimuth direction and limited swath. Since it is seeing in the azimuth direction as a smaller portion, so we can see in the azimuth direction we have the less area is imaged, and swath is also smaller. So in the spotlight mode, both in the azimuth direction and the range direction, the swath has decreased, but the resolution has increased in the azimuth direction. In the range direction, the resolution is same for the strip mode and for the spotlight. but the improvement of the resolution is only happening in the azimuth direction. Now third is the SAR mode. In the SAR principle, swath is increased by the use of antenna beam which is electronically steerable in the range direction. So this is the SAR mode. So while imaging this one, so it will divide its synthetic aperture time. Means if we want to have a larger swath in the range direction, so we can divide this synthetic aperture time to see the area in the range direction. So what it will compromise? It will compromise that synthetic aperture time in the direction of the azimuth with respect to the imaging in the range direction. So we can get the more swath in the range direction, but we can have the azimuth resolution coarser. Means we have the low azimuth resolution, but swath has increased. So this is called the SAR mode. In the SAR mode, the basic advantage is we can get the larger swath in the range direction by compromising with the synthetic aperture time. It can be done through the use of the antenna beam. Means one beam will see this one, second beam and this portion, third beam this. So if we have the multiple beams in the SAR, then we can use the SAR mode for the imaging. Now, what are the SAR image properties and interpretation? So what is the SAR image? The image is seen as a pixels. Pixels are digital numbers. Image is affected by noise. And image is interpretable based on the understanding of the physical process. SAR image interpretation is not straightforward. It requires some familiarity of the ground surface being imaged. So if it is the SAR image, so it is simply the pixels are the digital numbers which are complex in nature, and it is affected by the speckle, and it has the inherent physical process behind it. So we require some physics, and we have to understand some physics behind it. So basically the SAR backscatters depends on the two parameters. One is the target parameters and second is the sensor parameter. The target parameters are the surface roughness, dielectric constant, and local incidence angle. Sensors parameters are the wavelength, look angle, and polarization. So how we can see how the backscatter of the SAR image depends on this one. So basically, in the SAR image, the SAR backscatter contains the information about the Earth's surface which derive the reflection of the radar signal. As I said, like SAR image the electromagnetic radiation, it interacts with the Earth's surface, and the energy is backscattered towards the SAR sensor. That backscattered energy mainly depends on these two parameters, target parameters and sensor parameters. So these three are the target parameter and these three are the sensor parameter. Now we will look how these target parameters and sensor parameter will affect our SAR image. So first is the surface roughness. Okay. So for the SAR, actually, if this is a surface, then for the SAR it will have the surface as a smooth. It will follow the Rayleigh criteria. Like if the undulation, like this small h is there, if h is less than lambda by 8 cos theta, then we can say the surface is smooth. So if there is undulation or surface roughness is there, and if this value is greater than this, then it is a rough surface. If h is smaller than this one, then it is a smooth surface. So we can see if h is less than 0.272 centimeter. So for this one, like lambda 5.65 centimeter, and at differential angle of this one, so this will act as a specular reflection. Means there is the backscatter, very low backscatter, but for this one we have the moderate backscatter, and for this one with very much high backscatter. Okay, so for the SAR image, if the surface is rough, then we can have the higher backscatter due to the Rayleigh criteria, and Rayleigh criteria depends on this formula. H should be less than lambda by 8 by cos theta. H is the surface undulation, and lambda is the wavelength, and theta is the incident angle. Okay, so for the smooth surface, if the surface is very much smooth, then it is called the specular reflection, and we have the low backscatter. Moderate rough surface have the medium backscatter, and the rough surface have the higher backscatter. Second is the dielectric constant. Dielectric constant is a measure of the reflectivity and the conductivity of the material. The dielectric constant influences the ability of the material to absorb, reflect, and transmit the microwave energy. Higher the dielectric constant, higher will be the backscatter. Means dielectric constant influence the ability of material to absorb, reflect, and transmit of the microwave energy. So that SAR signal is very much depends on the what is the dielectric constant of that material. If the dielectric constant of the material will be higher, then we are getting the higher backscatter. Means the surface will look, and the surface will have the higher backscatter. Like water and metals have the high dielectric constant. Dry natural materials have the low dielectric constant. The presence of moisture increases a material complex dielectric constant. In the microwave range, most dry materials on the earth have a dielectric constant in the range of 1 to 8. Water, on the other hand, had a dielectric constant of approximately 80. So, if any natural object which has the dielectric constant of 1 to 8, if water will be present or moisture will be present, then the dielectric constant will be very much higher because water has the dielectric constant of 80. So the presence of moisture greatly increases the dielectric constant of the material. So if we can see soil, this normal soil will have the moderate backscatter from the SAR image, but for the soil which has the soil moisture in it, so soil moisture containing the values have the higher backscatter in the SAR image. So what are the properties? The dry soils have the low dielectric constant and low direct reflectivity. Wet soils are strong reflectors due to the high dielectric constant. Okay, so dry soils which have the moderate dielectric constant, but wet soil will have a higher dielectric constant. So we can get a lower backscatter energy for the dry soil, but for the wet soil we are getting the higher backscatter energy. Once a surface becomes entirely flooded, it acts as a specular reflector, resulting in the low backscatter. So flooded areas appears as dark in the SAR images. So once a surface is flooded, means water is there. So a calm water acts as a specular reflection. So due to the specular reflections, we have the low backscatter energy. So it will appear dark in the SAR images. Okay, so dry soil will appear as a moderate backscatter. Wet soil has the high backscatter, and the surface which are flooded also have the very much low backscatter. The reflectivity, hence the image brightness of the most natural vegetation and surfaces is increased with increasing moisture content. Okay, so in the SAR, the image brightness will increase with the increase of the moisture in the natural surface in the SAR image. And second is the local incident angle. So, and what is the local incident angle? So this is the SAR and this is the range. So what is the normal of the terrain which it is making with the slant range? It is the local incident angle. So this angle is the local incident angle. So what is the behavior of the backscatter? A smaller local incident angle results in the brighter radar returns. Okay, if the local incidence is smaller, then we have the higher brighter returns. And if the local incidence angle is larger, it will result in darker radar returns. Okay, so this is the effect of the local incident angle. Means if we have a terrain, so in the terrain we have different local incidence angle, and with respect to the local incidence angle, we are getting the different backscatter value in the SAR image. So if the local incidence is low, then it will have the higher backscatter value. And if the local incidence is high, then we have the darker radar returns. So how to interpret the SAR image based on the target parameter? So image tone refers to each distinguishable gray level from black to white, and it is proportional to the strength of the SAR backscatter. Means and the image tone in a SAR image is indirectly proportional to the SAR backscatter. Relatively smooth targets like calm water appear as a dark tones. Okay, so because of the specular reflection, the smooth targets like calm water appear as dark tones. Diffuse targets like some vegetation appear as the intermediate tones. Diffuse targets of vegetation or the rough surface are will be appear as the intermediate tones. The man-made targets like buildings, ships may produce the bright tone depending on the shape, orientation, and the dielectric constant. Okay, so the man-made targets have the high dielectric constant like buildings, ships, so that will appear always bright in the SAR image. So thumb rule is that like every man-made target will appear as the brighter in the SAR image, and we can have natural targets will be have the darker tone or means moderate tones. Okay, so like vegetation will have the intermediate tones, but relatively smooth natural surface will have the very much dark tone, and man-made targets will be appear very much bright in the SAR image. So we can say and the flat surfaces such as roads, runways, or calm water normally appear as dark areas in the SAR, since most of the incident radar pulses deflected away. So due to the small specular reflections, and these flat surfaces will appear as the darker tone. So this is, you can say, airport runway is there, so it will appear as the darker tone, means it will appear as a black. And this calm water like lake in the it will appear as darker tone. Okay, calm sea surface appears dark in SAR images, while rough sea surfaces may appear bright, especially when incidence angle is small. So that calm sea surfaces like this calm water will appear as darker, but when when any wind is passes through the ocean, then due to the Bragg scattering, which I will explain in the subsequent slide, what is Bragg scattering? Then due to the Bragg scattering, this ocean waves will appear as a brighter in the SAR image. Okay, so we have to understand various physical phenomena in the SAR image. Now, oil slick, like presence of the oil film smoothens out the sea surface. So in this SAR image, we can see this is the this oil slick. So it is have the very much high means very much high specular reflection. Means as the energy will as the SAR signal falls on this surface, then the energy will reflected away from the sensor. Means we have the specular reflections. So it will appear as a dark tones in the SAR images. Trees and other vegetation are usually moderately rough on the wavelength scale, and hence they appear as a moderately bright feature in the image. So these you can see the vegetations will appear as a bright objects as bright tones in the SAR image. Okay, like very much bright targets may appear in the image due to the corner reflector or double bounce effect, where the radar pulses bounces off of the horizontal towards the target and reflected from the vertical surface of the target back to the sensor. So like man-made targets, and if it is a vertical structure, then we have double bounce, and due to the double bounce, we have the higher backscatter. So examples are ships on the sea, high-rise building, and regular metallic objects such as cargo containers. They all appear as a brighter. So built-up areas, many made-with features are appear as brighter. So in this figure, we can see these ships. It will have the high values. So any man-made material which have the high dielectric constant will appear as the bright. So here you can see these urban features are appearing as the brighter tones, and these oil containers are appear as a brighter tone. So in this SAR image, we can say this is the sea, which is water as a specular scattering, which is appear as a dark one. And these are the man-made structures are bright in nature. This is the vegetation which is showing the moderate, and you can see these ships which is appearing as a very much brighter hair. So this is one of the way to interpret the SAR image due to is how the surface is, either it is speckle, it is a man-made, or it is a water due to the specular reflections, or due to the roughness, or due to the dielectric constant. So we have to see the various phenomena working behind the interaction of the SAR signal with the Earth surface. Now, I have told about the target parameters. Now they are the sensor parameters. Sensor parameter one is the wavelength. So backscatter is directly related to the wavelength of the microwave pulses as a function of the terrain objects. So radar wavelength should be matched to the size of the surface feature that we wish to discriminate. Okay, so what we want to see, basically if user want to have some of the analysis like soil analysis or ocean analysis, so depend on their application, we will choose the radar wavelength. So radar wavelength should be matched to the size of the surface. So if we want to have the smaller object we want to see, then wavelength should be small. Okay, so object appear bright if it is matched the size of the object matches with the wavelength. Okay, so if the size of the object will match with the wavelength, then we have the higher backscatter. So if we want to distinguish the smaller features, then we will use the smaller wavelength. So smaller features discriminator uses the X band. Okay, so we will use for the X band if we want high resolution images. Means if you want to discriminate the small targets or small features, then we will use the small X band. And if we will use the large features, then we will use the L band for the geological mapping type of thing. And for the foliage penetration, better at the low frequencies, use L and P. Okay, so this L band will penetrate more. So if we want to see the foliage, means in the forest cover we want to see anything, then we will use the L or P band. So and these are some of the ranges of the X band, C band, S band, L band, and P band. So X band it will vary from 2.4 to 3.75 centimeter, C band 3.75 to 7.5, S band 7.5 to 15 centimeter, L band 15 centimeter, 30 centimeter. So as this we can see, this is the wavelength is increasing. So this wave and the X band will have the lower wavelength and P band have the higher wavelength. So different satellites are associated, like X band is IIRS, C band we have the Reset-1, our Indian satellite, RASAT-1, 2, and Sentinel. S band is the SAR satellite is there, and upcoming satellite is and NISR. L band is of Pulsar and CSAT, and P band it is coming. It is an airborne, and in the future ESA is making the P band, and right now no spaceborne satellite have the P band. So when the wavelength increases, it will penetrate the Earth surface. So in the SAR image appears smooth if it will penetrate the surface. You can see the image in the C band and L band. As I said, as the wavelength increases, the penetration power increases. So that SAR signal will penetrate the Earth surface. So this surface will look smoother than this surface because it is penetrating the surfaces. So this is the appearance of the SAR image in the C band, and this is the L band, because the penetration power increases from when the wavelength will increase. Now one concept is the backscattering. In this ocean, actually when any wind is passes, then we have the ripples. Then these ripples, if the height of these ripples matched with the wavelength of the SAR signal, then resonance will happen and it will increase the backscatter of the SAR energy. And so if any ocean, if wind is passing, then this ocean will appear as a rough surface and appear as very much brighter object. Okay, so that due to that backscattering. So backscattering formula is lambda b is equals to lambda s by 2 sin phi. Lambda s is the SAR wavelength and 2 sin phi is the it is the incidence angle. So this is the formula of getting the wavelength, and this wavelength is, if it is matches with our SAR wavelength, then it will have the resonance in that, and the backscatter will increase. So the ocean surface, if it has very much waves are in it, then we have the very much brighter returns in the oceans due to the backscattering. Now another SAR parameter is the look angle. The look angle is the angle between the SAR slant range and nadir. The backscatter decreases as a function of look angle. As look angle increases, backscatter decreases. Okay, so as term of the look angle, as the look angle will increase, the backscatter will decrease. Okay, So for the large look angle, interact more with the vertical features, and the smaller angles interact with the horizontal feature. So depend upon our application, we will choose our look angle. So if in our soil analysis or in the crop monitoring, if we have to monitor the vertical features, means if we want to see the crop like sugarcane, then we will use the higher look angle for that one. If we are doing for the soil moisture type of thing, means only the soil thing we are doing, then lower incidence angle is more beneficial in the SAR image. So depend on the look angle, we can have our different application. Okay, so this is the one of the SAR parameter. Another is the SAR polarization. SAR polarization actually refers to the orientation of the electric vector of the electromagnetic wave. So radar system antennas can be configured to transmit and receive either horizontally or vertical polarized electromagnetic radiation. So we can have the single, dual or quad pole SAR system. Means SAR system can be configured in particular in particular polarization. So the SAR system can emit the electromagnetic radiation either in the H or V. So we can transmit the H polarization and receive the H. So we have the HH polarization and configuration. If we transmit H and receive V, then we have HV. If we transmit V and receive H, then we have VH polarization. If we transmit V and receive V, then we have VV polarization. So such type of system is called the quad pole system, which we have the four possible combination: HH, HV, VH, and VV. So what are the characteristics of this polarization? The vertically polarized waves interact with vertical structured objects. Okay. So and horizontal polarized have greater interaction with the horizontal features. So you can see if this SAR image, this is the horizontal polarization and this is the vertical polarization. Then the horizontal polarization enhances the backscattered of the horizontal terrain structures, and the vertical polarization enhances the vertical terrain structure. Okay, so these are the two basic polarization at horizontal and vertical polarization. And one more thing is that the vegetation is depolarize the signal. Means when the SAR signal having any polarization interacts with the vegetation, then there will be the volume scattering. So that will be, it will pass through the trees, leaves. So it will depolarize the signal. Okay. So means if we are emitting the H polarization, then the trees will depolarize the signal. Means if we are transmitting the H polarized, then tree will interact with the SAR signal and made that horizontal polarization to the vertical polarization. Okay. So and the trees will depolarize the signal. So if we use the SAR system which have the HV configuration, means it can transmit the H polarized data, but it can receive the V polarized data. Okay, so that system will have the high backscatter value for the vegetation. Okay, because vegetation is depolarizing. It is, if we passing the H polarization and it will depolarize and it will make that polarization to the V. And in our SAR receiver, if we capture that depolarization, then we can have the high backscatter. So vegetation will be appear brighter in the HV polarization. Understand? So these are three figures you can see, because HH polarization you can see this brighter object, it is showing the brighter objects, this one. In the VV polarization you can just see because of the ripples and these vertical features are enhanced. So these you can see the VV polarization, some brighter returns are there. But in the HV, due to the volume scattering and because the vegetation depolarize the signal, then it has the very much brighter returns in the HV. And you cannot differentiate the brighter returns from the urban building and from the vegetation. Okay, so these are three images which distinguish the SAR images in different polarization. Okay, so the same area in the HS polarization, VV polarization, and HV polarization. So it is showing the volume scattering. So what are the dependency of the polarization and the SAR backscatter? Then the radar backscatter as a function of the polarization. So BV have the highest backscattered, then HF, and then VH. Okay. So now we can see, and this is the different polarization concept. Now we can see the SAR geometrical properties. Okay. So basically, it has three distortion. One is layover, foreshortening, and shadowing. Geometric properties are very different to the optical remote sensing and are key to the understanding SAR remote sensing. Since SAR systems are the side-looking distance measuring system, thus the geometrical parameters are the incidence angle, local incidence angle, and look angle. The side-looking geometry of SAR results in the severe geometrical distortion. Okay, because SAR is a side-looking sensor, then it has very much geometrical distortion. These distortions are called the layover, foreshortening, and shadowing. Now, one question is why SAR is side looking. Okay, so if because I have already said that SAR will have recorded the range, so it will record the range. Okay, so if two targets are here and SAR has this type of beam, means nadir looking. So in this nadir looking, you can see these two targets have same range. So SAR will not able to distinguish these two targets as separate two targets. So there will be the range ambiguity. So SAR is not a nadir looking sensor. So how to resolve this one? So this right-left ambiguity is solved by looking the side-looking geometry. So if it is looking at the side ways, then these two targets have different range. This R1 and R2. You can see this R1 will be smaller and this R2 will be larger. So we don't have this range ambiguity. Okay. So if it is a nadir looking, we have the range ambiguity because the both targets have the same range and the SAR will not distinguish two targets separately. Wherein in the case of the side looking geometry, the two targets have the different ranges and there will be no range ambiguity. So this is the basically difference between the SAR and the optical geometry. This is the SAR side looking and this is the optical nadir looking. So here, if three targets are there, A, B, and C, then this A will focus here, B will focus here, and C will focus here due to the lens. Okay, this is the optical sensor. So this is the sensor geometry in the optical sensor. But in the SAR, it will focus on the slant range. Okay, so basically the SAR sensor will focus on the slant range direction. So this is the A dash, B dash, and C dash. Okay. So this is the SAR geometry. Okay, so we have this one. If this is the azimuth direction, then this is the nadir. And if this is a beam, SAR beam, then how much angle it is making with the nadir, it is called the look angle. And if it is a horizon, then how much it is making angle with this horizon is called the depression angle. This is the range direction, and this is the near range. This is the far range, and the distance between near and far range is called the SAR. This is the beam width, and this is called the incidence angle, which is the SAR will make with the normal to the surface. Okay, this is the incidence angle. This is the look angle. So if the surface is plane, then this look angle is equals to the incidence angle. Otherwise, it will not. Okay, so for the planar surface, this look angle will always equal to the incidence angle. Okay, so these are some of the geometrical parameters of the SAR. So SAR has the relief displacement. Relief displacement due to the different imaging geometries of the SAR and optical system. Topographic displacement differs between the systems. So horizontal displacement of the SAR system is higher near nadir and decreases with incident angle. Horizontal displacement can be severe and smaller incidence angle. In contrast, topographic displacement for optical systems increases with incidence angle. So you can see there will be relief displacement in both optical and the SAR sensor. But in the optical sensor, it will be lesser. In the SAR sensor, it will be a higher. The formula of the relief displacement in the SAR sensor is S cot theta, and in the optical sensor, it is the S tan theta. So you can see because SAR has the side-looking geometry, then if we have the look angle of 10 degree, 20 degree, and 85 degree, we can see the relief displacement is very much higher. So geometrical distortions will be very much higher, because this is the, and due to this relief displacement, this object will be come here. So there is geometrically it will be not correct. So it will displace from this position to this position in the SAR images, because we can see at the lower angle we have the highest displacement. So if we have the 10-meter angle, and we have the 100-meter height, 100-meter height for a 10-degree look angle, we have the 567-meter distortion if we have a local we have the low look angle, and this will decrease if we go from near range to the far range. Okay, now you can see the optical sensor. The formula, same formula. If we have the maximum angle of 45 degree also, this it can be go up to the 100 meter. But for the SAR sensor, it can go to the 500 meter. So relief displacement in SAR images is very much high. Due to that, we have very much geometrical distortion. What are that geometrical distortion? It is foreshortening, layover, and shadow. Now, what is foreshortening? Foreshortening is the appearance of the compression in the topographic features in the scene. Means the features appear to be tilted towards the radar. The foreshortening is maximum when a steep slope is horizontal to the radar beam. So you can see, if this is the sensor, then if it is this is the two positions C and D, then these two positions will drive at same place. Okay, so due to this, we have a higher brighter return, because both positions are written here on this and C dash D dash. So it is called the foreshortening, the appearance of compression, because this feature is compressed to this position. Okay, and this position also compressed to this one. So this compression due to the terrain and due to the side looking geometry, it is called the foreshortening. So if we have the SAR image, means slant range image, then foreshortening appear like this one. And if our ortho image, in the foreshortening, we can see this spread is there. So using the damp, we are doing the ortho rectification. So this is foreshortening after correction. So there will be a spread. So if we are working on the slant range image, the foreshortening maybe look like this one. That if we are working on the ortho images, then the foreshortening will be spread due to the correction of the data, geometrical correction we are doing, and putting the values of the position in the correct position. So this is called the ortho rectification. Second is the layover. Layover is the extreme case of the foreshortening and occurs when the incidence angle is smaller than the local topographic slope. So in the layover, what it is happening, A and B, these positions are reversed. Means B will be come here and A will come here. Means this position will reverse. Like A should come first, but A is coming last. So these positions are just reversed. So layover is more prevalent for being geometry with smaller incidence angle. Means it is a complete orientation of the mountainous terrain. Okay, so this is the layover. And shadow is the areas on the ground not illuminated by the SAR because of the beam geometry and scene relief. Since no return signal is received, radar shadow appears very dark in tone in the SAR image. So if this is, so here no energy will be appear. So you can see this is the shadow area. Okay, so these area where the SAR energy cannot go, that is called the shadow areas. Here shortening. So towards the near range, we have the higher layover. Okay, so as we go to near to far range, the layover is decreasing and foreshortening is increasing. So you can see this is top bottom. Okay, it is coming, top is coming first and bottom is coming last, and this layover will decrease, and ultimately it is coming, but we have the foreshortening effect. So foreshortening effect will be appear in the far range, but layover more prevalent in the near range. Now what is speckle? Speckle occurs in the SAR image due to the coherent interference of many scatters within a resolution square. Bright pixels are formed due to the constructive interference, and the dark pixels are formed due to the destructive interference. Okay, so due to the SAR is a coherent device, then there will be interference in the signals. So where there is a constructive interference, we have the SAR signals are in phase. Otherwise, in the destructive interference, that are out of phase. So this constructive and destructive interference will appear as a bright and dark spot in the images. So if this is the interference formula, then we can have the constructive interference and destructive interference. Here you can see that dark pixels are there. So this is the original image which have the speckle, and this is the denoised image, means we are applying any speckle filter, and this is the smooth image. Okay, so this speckle will coherent inherent in the SAR images due to the coherent imaging, because it is thus all the signals are coherent in nature. So these are some of the SAR sensors: CSAT, IIRS1, and GIRS, IRS2. So L-band is the CSAT, and PALSA is L-band. TerraSAR-X is our ISRO satellite. VSAT-1 is launched on 2012. C-band, it has the quad polarimetry and hybrid polarimetry, and these are different polarizations. So you can see the different feature in the SAR image. Okay, so you cannot tell at this resolution which is the SAR image and optical image. So you can see both are looking similar only. So which is the SAR image? This is the SAR image, and this is the optical image. You can see this, as I told, that man-made objects will appear brighter. So you can see this bridge. This is a Mumbai area, and you can see that urban area are appearing as brighter, and this bridge is appearing brighter. But in the optical image, you cannot distinguish this one at this resolution. They are both in same resolution. Okay, so this is the SAR satellite. This is the optical satellite of the same area. So you can see these urban features are showing the brighter returns here. So this is the image of reset one. It is of 18 meter. So you can see this urban features brighter near Mumbai area. You can see the lake. This showing as a bright darker tones. Usman Sagar Lake, Hyderabad, Sentinel-1 image. You can see the structures. So this is the very much high resolution, 1 meter resolution. So this is the optical image, TerraSAR image, and this is the SAR image. So you can see due to the geometry and that lower and shadow, the structures are not appearing like that. So you can see some of the structures we have to see. Okay, how much is the look angle and how is the due to the look angle, the geometrical distortions are in the images. And you can see the urban features. This is the TerraSAR image of Toronto of 1 meter. You can see this is a flyover, and this all are the some of the lampposts which is appearing as a brighter returns. And this you can see the electric transmission tower. It is a 0.6 meter Barcelona. You can in the field you can see this is the higher. It is showing in the agriculture field the electrical transmission. This is the airport in the Sentinel and Sentinel-2. You can see this how it is appearing, because due to specular reflection, this airport is appearing as a runway is appearing as a dark tones. This is the New Delhi airport of Sentinel-1, 10 meter. This is the higher resolution of 3 meter of TerraSAR-X image, Barcelona airport. Okay, so you can see. Now this is of allows 2.6 meter same Barcelona. This you can see the optical satellite, and this is the SAR satellite. So this you can see the aeroplanes and the how the aeroplanes are look like. So basically, and the SAR images does not give proper shape, but it can detect very well. It will give the brighter returns, but shape may be not proper due to its geometrical properties. This is the Mumbai seaport of 10 meter resolution, and this is the Karachi. You can see this is SAR image, and this is optical image. Because you can see in this image the bright and the urban areas, you can easily differentiate man-made targets as a brighter tones. And this is the seaport of the Vizag area, and you can see this is a ship of 0.5 meter resolution. So and this clearly you can distinguish the ship in the image. Thank you.